Mike. Good morning. Hope you're all doing well. If you're in programming algorithms 2, you're probably breathing a sigh of relief that the last project is over and now you have a little bit of time to build up to the next one. Morning, Tyler. So I'll show you what's going on in this class. Remember, at Butte College, we don't take Thanksgiving week off, so most classes are should have somewhat close to their normal routine. And I know that can be irritating, but that's how we do things. So, but in our class, which hopefully comes as something that's welcome, we are in week 14. I just want to show you. If it'll let me show you. So we don't have a discussion this week. We don't have a homework this week. We don't have a lab this week. So all we're going to do is try to get ourselves a good, strong start on the second project, which in this class is the second and final project. If you're taking both this class and Programming and Algorithms 2, then you have a challenge here in the last few weeks to juggle your time between the two because they both have projects. So hopefully what we do today will give you a good strong start and you'll sort of take off and run with it as much as is possible before you start having to worry about projects in another class. So that's my hope for you, but that's the whole week 14 is on this one page. There's no discussion, there is no homework, there is no lab, but I hope that you'll follow along with me and begin developing individual project 2. I will post the lecture as normal because I'm going to actually try to get you spun up on this project. You will have this as a reference if you need it later. So let's open up project 2 and just do it. And I don't mean complete the whole project, I just mean get into it. So this looks awful scary, but one of the reasons why there's a lot more words than normal assignments is because I want you to have access to this information about what is the project about. So this whole description section is just trying to describe for you in words what the project's about. So in terms of the technical skills, we'll be practicing using the x86 addressing modes, and particularly the array ones, which are weird, so the indexed and the scaled index addressing, which of course you have to combine with dereferencing memory address to get data. So that's a big part of it, using or managing dynamic memory, which in HLA is malloc and freeze. We haven't done this part yet. This is sort of the last week or so of the semester. So what I recommend that you do is you develop a project 2 without low-level decisions and loops, and then like the closer you're finished with the whole project without low-level decisions and loops, the better, because when we get to that last week and we introduce low-level decisions and loops, you can make an informed choice about how much of your life to put into converting your project to use low-level decisions and loops. So if I were in your shoes, that would be a goal I would set for myself, is finish the project without this stuff. And if you don't know what it is, that's fine, so you won't use it. Try to finish the project without this stuff, and then you can, during the last week of classes, you can decide how much work to put into implementing these. The stack, so using push and pop to preserve data using the stack. We will of course have some arithmetic in here, and then of course, so what this project really does is it forces you to use the skills and techniques you've been developing the whole semester. That's all that bullet list really shows you. Okay, so we're calling this program a spreadsheet, but it's not actually a spreadsheet. It's just one row of numbers that we can apply operations to. So if we were to go on for another semester, let's say, we might expand this one row spreadsheet into an actual spreadsheet with multiple rows. But it's kind of like a spreadsheet in the way it functions, because you can take a set of numbers and apply an operation to them. So you can, if you've used Excel, you can mark a set of numbers and you can compute their average, or you can identify the maximum number in that group or the minimum number in that group, or the sum of the numbers. So anyway, we're going to do sort of a spreadsheet simulation with a single row of values, and then at the end of that row there will be an operation that we are applying to that row. I'll show you in the screenshots below. Okay, so set of numbers and an operation that we apply to that set of numbers. So we're going to allow the user to specify how many cells they have in their row. That gives us an excuse to practice doing dynamic memory allocations. We're also going to have the user choose a data type. So our spreadsheet will either be operating in int8 mode right now, or int16 mode right now, or int32 mode right now. So our user will have the option of selecting which of those three data types they want their little one row spreadsheet to be in at any given moment. If they want to switch to a different data type, they're going to have to basically say, I'm done with this, and they want to create a new one row spreadsheet, at which point they can select the data type that they want. Okay, Malix. Operations. So we already did a maximum value algorithm, and we'll use a form of that to solve this project. You'll see in the screenshots, but basically displaying the result of applying the operation to the numbers, and also what the operation is. So there should be a label at the end that says this is a sum, and this is what the sum is. I'll show you this in the screenshots again. We also want to detect overflows, because we don't want to tell the user that we're showing a sum when we just accidentally computed an overflow. When the user resets, we will use free to release the memory, and then we will take the user back through the process of selecting a type, telling us how many cells they want, and then allocating new memory for the new spreadsheet. They can quit anytime. And then the current state of the spreadsheet, the one row spreadsheet, should constantly display. And then we're going to add this functionality that we can let the user can toggle their output and show all their values, all their data in binary, or all their data in hex, or all their data in decimal. That's a part of sort of reviewing the numbering systems. Okay, so that seems like a lot, but it's not that bad if we get a good start and we just sort of tackle one problem at a time. You'll find that it's highly repetitive. Okay. Oh, I actually, instead of giving you screenshots, I actually gave you executables. Let's see what that looks like. Ooh, that was pretty cool of me to do that. So instead of giving you screenshots, I made it so that you could download and actually interact with my program. Let's see if the Windows one works. Download it. You're probably going to get this. Don't say don't run, because you want to run it. So if you got more info, yes, run anyway. All right, so here we go. So we're going to work on some parts of this today. So notice how my program does it. Right at the very start, it asks the user, how many cells do you need? And having one cell would be kind of pointless, so we're going to tie them down to a minimum of 2. And we're going to max them out at 10, because that's plenty enough to kind of prove that the algorithms work. So I'll say 5. Now we have to say, okay, you want 5 cells. How many, what data type do you want in the cells? Oh, you don't? That's true. Okay, thank you guys for that. Let me restart it and do that again. Okay, thank you. Sorry about that. So here's the running program. Where we're going to interact with it. So I compiled a Windows version, which is the one that I downloaded. I compiled a Mac version if you're on a Mac, and I compiled a version that you can drag into your virtual machine and run it there if you want. Okay, so we're going to work on parts of this. So we ask the user, how many cells do you want? I'll say I want 5. I want to work with 5 numbers. What kind of data will those numbers be? I'll say int 16s. Okay, now it says 12 bytes are allocated, and this part confuses people, so I just want to try to explain it, and then we'll look at it in code also. They chose 5 cells. They are 2 bytes apiece, because they chose type 2, but we allocated 12 bytes. Now, why is that? Well, 10 bytes of those 12 are for the data, but we allocated an additional 2 bytes because we need the data plus a cell to hold the results of our calculations that we're going to perform. So we have their 5 numbers plus the cell that's going to hold the maximum or the minimum or the average or the sum based on what they've selected. So we actually have to allocate an extra cell of that size so that we can do calculations on the first 5 of them. Okay, so here we go. The default is displaying the values in decimal. Here's the 5 values. And then I defaulted to show the sum. So this sum is that 6th cell, which caused the 12 bytes to be allocated. So there's the 10 bytes that they asked for, plus an additional 2 so that I can run up calculations. So I defaulted their display to decimal, and I defaulted their calculation type to be a sum. And then I have a menu of options for them so they can edit cells. So I want to edit. Notice here, by the way, that it's asking the user cell number 1 through 5. So it's kind of spoofing a little bit because the actual offsets are 0 through 4. But let's just go for the first one. So here's a little tell, cell number 0. So cell 1, my output, that's not the best, is it? And then it is asking me for a new value. So let's just say 6, I don't know, I'll say 10. Okay, so now I've edited what was adjusted to be cell 0. I put the new value 10, so when I press enter, so notice that it comes back and it redisplays the value. It ran the calculation to produce the sum, and then I'm back to my menu. I can switch, for example, the way I'm presenting the values. So let's switch to binary. So now all the data is shown in binary, not just the data cells, but also the calculation cell, that extra cell that I allocated. I can change the calculation. So let's change it to be the maximum value. I'll switch the presentation to hex just to show how that works. And then I'll switch notice, by the way, there's 16 bits per value, which is divided by 4 bits per nibble is 4 nibbles, so that's why that. Anyway, if we do reset, it goes back to the original, okay, you want to start over, how many cells do you want? Oh, I want 10 this time. What type? Int 8. So it allocated 10 bytes for my data cells, and then it added an extra cell to hold the calculation. So that's how the program runs. So anyway, those are all available as downloads. They're linked to the project, so that if you want to see a working one and kind of use it for its ideas, you can do that. I made one for our Ubuntu system. I made one for Macs if you're on a Mac, and I made one for Windows if you're on a Windows, so you can see how it runs. Okay, so that's just to give you an idea based on my own implementation of how it works. How are we on time? We're fine on time. I need to switch my view. Okay, so I'm going to switch my view, and I'm just going to sort of begin implementing something that's very similar to that and leave breadcrumbs for myself about where I need to add implementation. So let me switch the view to my virtual machine and go log in there and start developing some stuff. Why does this thing not look good? It just doesn't look good. Yeah, it'll be okay. So we're done with one array. So there's a question if we are done with one array and then we free memory and allocate another array. So it's a good question. So when we free one array and we reallocate another, what's actually happening there? Why are the values still there? So if you free an array and then you allocate again and you see the same values, it's because you ended up getting the same block of memory allocated to you. So we'll deal with that. How do we scrub the data between one allocation and the next so that the old values don't look like they stayed around? And we will deal with that. That's right. So Gershvax points out that in the week 13 program, if you ran it multiple times, you would notice that each run of it probably retained some portion of the values from the last run. And that's because the new allocation is actually just being allocated right over the top of the original allocation, and the data is still there because it wasn't being overwritten. We'll look at how to deal with that. Okay, so I don't. Apparently I already have one called spreadsheet. Whatever it is, I don't want to lose it. Okay. All right, so I'm going to begin implementing spreadsheet, but before we do that, let's address in a better way, the question about how do we scrub out the old data between allocations. So let me put Firefox back up, my browser. Let's go look at the HLA standard library documentation. So I'm just going to Google that, HLA standard library documentation. And then we're going to look for the memory module. So if we scroll down, memory, not mmap, not memory map.io, but memory. This is the module that gives us some additional options. So there is a mem.alloc, which is basically the malloc that we've been using, but let's go find a more interesting one. Okay, but let's look at this one real quick. So effectively we've been using this one, even though ours just says malloc, but effectively we've been using this one. Let's just read through it a little bit and see what it says. So allocates a requested number of bytes that we're familiar with. If successful, it returns a pointer to the allocated storage in EAX. So that's why we immediately take EAX and copy it somewhere, is because that EAX is the pointer to or address of the allocated memory. It can throw exceptions, but we're not going to worry about that. Okay, but here's the key part. Note that this function does not initialize the block of memory to any particular value when it allocates it. In particular, do not count on this function setting the block of memory to zeros. So the form of allocation we've been using, all it does is allocate memory, and if there's already data there, then you're going to get whatever data is there. That's the malloc we've been using. Now let's scroll down because there's an alternative. It's this one. mem.zalloc. So mem.zalloc, it takes a number of bytes and returns a pointer. But let's see what it does. Allocates the requested number of bytes, good, and zeroes out the data storage allocated, even better. So if we use mem.zalloc to do our allocation, we actually get the underlying memory zeroed out, even if there happened to be data there already. So we're going to use that one. If successful, returns a pointer to the allocated storage in EAX, and we're going to assume that it's going to be successful because it should. So if we want our memory that we just got allocated to be guaranteed to be zeroed out, we want to use mem.zalloc for our allocation. So we're going to do that in our program. Excellent question, Garsavan. Okay, so here we go. We're more or less, I'm just going to try to mirror what's going on in the program that I just saw. I noticed, for example, that there's this outer loop that will come back and ask them these questions. So I'm just going to build that in right from the start. Hold on, I need to do some screen organization so I can see you guys. Okay, so it first asked us, 2 to 10. And then I'll also kind of point out to you where you should be doing improvements. How many cells do you want? 2 to 10. But we'll just start with some basics, and then we'll start sort of improving our design to use procedures. Let's get that as a unsigned 32. Now there's a reason for this that I will try to show you later, but let's get it as a U32. So we have that. We have now we know how many cells they want in EAX. Our code does not guarantee 2 to 10, so that's a problem, and we're going to fix that here in just a second. But the basics is, how many cells do you want? Now we have to increment their selected number of cells by 1. And the reason we need to do that is because they have the data cells, and then they have one extra cell to hold the results of calculations. So however many number of cells they want, I need to increment that by 1 because I need that one extra cell to hold calculations. Okay, now I'm going to say standard out.put. Select the data type. I might just do it like this. So now we select a data type. If you use unsigned 32s in this program, you'll find places where this makes life a lot easier. Now I'm going to this should raise red flags immediately, like something's terribly, terribly wrong already in my program. Does anyone see where I just screwed something up? So I'll give you a hint. Well, that's fine. So Tyler is asking, and you should check, should this be assigned integer? And it doesn't need to be, because all we're really specifying is a code, basically, that represents a data type. So since the values are 1, 2, and 3, they can be unsigned, even though I know that they're representative of signed integers. All right, so good on Gersava. We just did a calculation up here of figuring out how many cells they want, plus the one that we need for doing calculations, and then we immediately overrode it. So we're going to need some variables. So this is a good place to remind yourself, like, why do we use variables? Well, so it's that we don't lose data, which is particularly important in assembly. So I need a variable for this. So I am going to create I'm going to put M on the front, just in case HLA uses some of these words. So M size is going to be an UNS32, and it's going to represent the size of the number of cells of my array. I also want M type. I'm messing these all up. This will be the code for the type. So remember, you have to sort of map a code to a type. So M type 1 in my program is going to mean int 8, and I will use that in places to figure out when I should be doing int 8 stuff. M type of 2, should take that comma out of there. An M type of 2 is going to mean int 16, and an M type of 3 is going to mean int 32. So I need a variable that actually tells me which of the data types, because that will inform me about doing things like typecasting and some other stuff. Okay, so let's get rid of this ink for now and worry about the two separate problems. So the first problem is to offload the size of the cells, the number of cells they wanted, and then we're going to do the same thing here. So all this is a code. M type, if it's 1, then I know in my logic that they are working with int 8 right now. And I'm going to write all my logic around that. And if M type is coded to 2, then I will know when I write my code that those will be int 16s, M type of 3. So there's no other way to sort of keep track of which of the types they selected unless I have a code for that. So that's what M type does. Now I also notice I'm doing getU32 twice, and it would be nice if I prevent my user from making mistakes. So I'm going to write a procedure for this. You've seen this procedure before. I could go copy and paste it, but I'm just going to write it real quick because it's easy to write. So what I want to do for my two procedures, for these two routines, I want them to be robust, and I also want them to do range limiting. So I'm going to use the same pattern. To get any UNS32, I want to require a prompt string. What do you want me to print out to tell the user to type stuff now? I'm going to need the minimum value as an UNS32 and the maximum allowed as an UNS32. So now I can convert these two to this procedure, and I can make the user input handling be very robust. We will put this in a forever loop. we will print out the prompt. And then we're going to use a try catch to handle the problem that they type something dumb. I'm having typing troubles today. So we get the basics set up, right? This try and try, all that does is guarantee that what they type in can be an unsigned 32-bit integer. If they type their name, it's going to fall into this exception and complain. If they type a negative number, it's going to fall in this exception. If they type something that's way bigger or way smaller than an UNS32 value can be, it will cause this exception. So that's the basic handling. Now I add so if they did okay with the input, they didn't type something stupid like a negative number or their name, now I can enter into the unprotected section where I make sure that I got the value that I want. So basically, we're going to flush the input at this point. And then we're going to check our range. So if we're above the min and below the max, then we're done. And this break if breaks us out of the nearest loop, not the try, but the loop. Now if we don't happen to break, then the flow of execution is going to come to the next line down, and we can take advantage of that. I want that all in one line. Okay, there we go. You've seen this function a whole bunch of times, but it's probably been a while since you thought about what it's doing. So we're taking advantage of the try exception, any try, n try of HLA to guarantee that we actually get a U32, and then we're taking advantage of this short circuit routine, break if, to check the range. So if their input is in the allowable range, then we immediately break out of the forever loop and the function's done. If we don't break here, then the flow of the program is going to go to the next line down, at which point we know, well, they put in a U32, but they didn't put in what we wanted, so we're going to complain at them, at which point the flow of the program will hit the bottom of the loop and restart. So there's that. Now, there's something else that I know from experience. This procedure is supposed to come back with EAX. So I don't want to push EAX because I want the procedure to actually affect EAX. But I know from experimentation that these other critical registers can be affected. So I know from experience I should push those three aside and pop them off at the end in the reverse order, so that if they're being used somewhere else in the program, that somewhere else doesn't break. But if you call this procedure, you're getting an input value in EAX. So that's a lot of coding effort. I wish it folded. But this is how I would go about developing this. The moment that I see myself repeating something, I'm going to put a procedure in. So now I can just replace this with get uns32, keep my original prompt, but now I also have the power to disallow anything that's not in my desired range. And then I can do the same thing for this other. Use my procedure, keep the prompt, but also tie the user down to between 1 and 3, and now they can't screw that up. So now I'm getting I have a robust program in development. Okay, so now we have how many do they want. Now we have the type that they want. Now it's time to do a calculation of how many bytes do we need. So to do that calculation, I'm going to put msize back into EAX. So EAX is going to be used as the middleman. So I'm going to compute the number of bytes into EAX. So remember, they just told me like I want 5 cells, but I know I need 1 extra. So I'm going to allocate 1 more than they asked for. So now we know if they ask for 5, we're going to give them 6. If they ask for 10, we're going to give them 11. We're always going to have that 1 extra cell to do calculations into. Now it's time, now that we know how many cells we need, now it's time to scale it up for the data type. So here's where we use mtype. So if mtype equals 1, that code tells me that I have int 8s, which means that I don't have to scale because this is just 1 byte per. So if they ask for 10, I'm going to allocate 11 times 1 byte per is still 11. So in fact, I don't even care about that one, do I? I don't think I do. Let's see if we can avoid the work altogether. Let's just start with type 2. So now we're scaling up. We're scaling up to the number of bytes that we need to allocate. I'll just show you why I didn't do that first part real quick. So why did I skip type 1? So this is fine. So why did I just kind of not bother with mtype of 1, the int 8s? Because the size is 1, right, Tyler? So all I'm really doing here is mulling EAX by 1, which doesn't hurt anybody, but there's no point in it. So if I realize, whenever I realize that the math I'm doing doesn't result in doing any changes, the size of int 8 is 1 byte, and 1 times EAX is EAX, I can just not do the work. So I just don't even ask the computer to put the effort in, because what's the point? Okay, so what do I have? What I have then at the end of this if, else if, I have in EAX the number of bytes that I need. So size tells me the number of cells. Type tells me what kind of data goes into each cell. Now I do this third section, which is I need to now compute how many bytes does this mean. So I put size back into EAX. I increment it by 1 because I want the number of cells requested plus an extra 1 for doing calculations into. And then I check to see if I need to scale the number of bytes. So let's say they ask for 10. I'm going to allocate 11 cells. 11 cells of int 8 is 11 bytes, so I just leave it alone. 11 cells of int 16 is 22 bytes, which is why I do this mul. 11 cells of int 32 is 44 bytes, which is why I do this mul. So when I get to the end of that thing, I'm going to mem.zalloc, and remember the cool advantage there, which is what Gersebach led us to with their question. That guarantees that whatever happens to be sitting in memory that we get allocated is zeroed out for us, which is quite nice. So I'm going to allocate this number of bytes that I just computed, and then I need to move that somewhere. So this is a pointer, which means I need a d-word variable to store it long term. So I'm going to go back to my static here. Give myself a d-word variable. I'm going to call it marray, like my array, my type, my size. That's going to be where I hold that pointer. And the requirements say that I'm supposed to spit out how much I allocated, and before I actually do the allocation is where I need to print that out. Because once I've done the allocation, my EAX gets overwritten. So let's put it here. And we'll say allocating. And type 132 EAX, so we see it as a decimal, bytes. And then we store. So let's try it out a couple of times just to see what happens. Oh, trick. So let's make ourselves a little pause procedure. Hopefully I'm not jumping around too much that it's painful. So there's my whole main. I've done the first part of the program. Ask them how many cells they want and read that in. Ask them what type they want and read that in. I have variables for both of those. Now I compute the number of bytes that I'm going to need to allocate, which is the number of cells plus an extra one for doing calculations into. And then if the type is 2 or the type is 3, I need to scale up for those number of bytes. So I just multiply to get that. Then I output how many I'm about to allocate. Then I do a zalloc on them, which guarantees that all those cells get zeroed out. And then I store the address of that allocated memory in marray. Let's give ourselves a little pause procedure, because I can imagine this is going to be useful. So this is an HLA library routine. It's read with a capital L. So very important that you notice that capital L. Read line, basically whatever they type or nothing, it reads everything up to and including when they press enter. Read the whole line of input, even if the whole line is literally just them pressing enter. So it's a good just throwaway input, and then you want to make sure and flush. So all this does is cause the program to hang. Uh-oh, you notice that pause is lit up? That means that the language uses that word. So let's change that to be, I'll call it hang. And then it didn't light up, so that should be a legal word. So that's all this does. It prints out press enter to continue and then forces them to type at least enter before it allows them to proceed. So this is a good way to cause the program to sort of hang up and let the user collect themselves before continuing. So we're going to put that down here. Hang the program. The other thing that we're going to do down here at the bottom is we're going to free the array. So we're literally just going to allocate free, allocate free, allocate free, allocate free over and over and over and over and over again. put a message so we know that happened. Right now, that's all this program is going to do is allocate memory, free it, allocate memory, free it, allocate memory, free it. Just so we can make sure that we understand how it's supposed to work, and then when we're looking to see how many bytes it's allocating, that those make sense. Notice that I typecast that EAX because I want to see the decimal for the number of bytes. I don't want to figure out in hex what does that mean. Okay, so I'm going to compile and run mine. I'm going to take that line out. So it's going to go through that whole routine over and over and over and over and over again. I have this hang there just so I can stop and read the screen before it continues. All right, here we go. Line 42. What? At line 42, expected a colon. I'm not seeing it. Let's debug. So it's complaining about line 42. I'm going to start just by commenting out the guts of this procedure and see if it's in here that I've made a mistake. No, now it goes to line 51. Possible undefined get uns. Alright, somewhere I've typed get uns. I see it. So I don't know if you saw, but once I commented out, I was getting an error on line 42 for who knows what reason. Maybe I forgot to save or something, but once I commented these out, then it actually went to the right line. Maybe I'm missing something. Alright, so there's the prompt. So if I type 3, my size is going to be 3. If I type 1, then what should happen is my type is going to be 1, my size is going to be 3, and when it goes to compute the number of bytes, it's going to take my size of 3 and add 1 to it, so I'm going to have 4. It's not going to scale the bytes from 4 to anything bigger because I selected type 1, so it should allocate 4 bytes. So that's good. That's what I wanted. So keep going. I'm just doing a small number, but we could do a bigger number if we wanted. 10, so let's try type 2. So it allocated 22 bytes, is that correct? Well, it took 10, that's the size. Type 2. So when it went to compute the number of bytes, it added 1 to 10 and got 11. Multiplied that by the size of int16, which is 2 bytes apiece. So that's 11 times 2 is 22, and that's what it allocated. And here's the hang procedure, just waiting for me to press enter. So let's try something randomly. So if I type say I want 6, and I choose type 3. So what's going to happen is type 3 is 4 bytes per cell. So it's going to take my 6 size, add 1 to it, that's 7. Times 4 bytes per cell is 28 bytes, is what it should allocate. So, as far as I know, that part is working just fine. I have no way to exit this program, so I'm just going to do Control-C to get out. You can see Control-C kind of printed that way. So, we are already far enough into this program that we're doing some critical pieces. I'm also, as I go, you might not do it this way, but as I go, I'm adding procedures to fill a need. You're going to have a lot. If you do it right, you should have a bunch of procedures in this program. I think we have time to at least start one piece. So right after this hang down here, press enter to continue. So what should happen now? What should happen now is that you enter the working with the spreadsheet portion of the program, which is another loop. So you're going to sit in this loop for a while, working with your current one-row spreadsheet. So we allocate one, then we work with that spreadsheet for a while. When they say they're done working with that spreadsheet, either because they want to quit or because they want to do another one, then we'll break out of here. We'll free their array and start the whole process over again, although we're going to need some way of detecting whether or not they meant to quit. But we'll worry about that in a second. So anyway, this inner loop part, the outer loop is for creating a spreadsheet and then creating another spreadsheet and then creating another spreadsheet. So we get it all set up. Then this inner loop, we work with our spreadsheet for a while. Once we are done working with the spreadsheet, we free it, and then we cycle back around and create a new one. That's how this works. So the first thing that this is supposed to do is it's supposed to print the current state of the spreadsheet. So you should have a print procedure for this. It will make your life a lot easier. You've actually done this one. Print, so we need the address of the array. We need how many cells are in it, and we also need what data type it is so that our print procedure knows which kind of typecasting to do and how much to scale to access the memory. I'll start this one, and this is where I'll sort of end the day. So we need a print here. I'm also going to hang the program in here for experimental purposes. But anyway, just make note of the fact this program is nowhere ready for prime time, obviously. It's a work in progress. I have to hit Control-C to get out of it. We're just sort of building up pieces. So a print routine. Given the address of an array, its size is an UNS32, and its type as an UNS32. So let's go give ourselves a print procedure. So the array, which will be a D word, the size, which will be an UNS32, that's to match our statics, right? So if we pass in on an array, that's a D word. If we pass in a size, that's UNS32. If we pass in the type, that's UNS32. So we just make sure that those match. Type, oh, see how that one lit up? Ooh, is this scary to anyone? This is like the Go style. A for the array, S for the size, and T for the type. It's very cryptic. Oh, I don't know if you noticed, but where we will pick up with next time is that the program is supposed to toggle between different output styles, so we're going to have to deal with that. But for now, let's just do decimal, and then we'll refactor as we need. So we're going to need to move that to somewhere where we can use it, and then we'll simply for loop. I'm probably just going to push all of the registers because I'm not doing any calculations and I'm not getting any user inputs in here. So we can save ourselves a little bit of pain. Let's just make sure we don't damage any registers around this procedure. Alright, so now we'll just start printing some stuff. So we will, here's the tricky part. Let's print out the, at least I'm going to print out the index followed by a space. So all that does is print out which index am I on right now, 0, 1, 2, 3, 4, however many. Now we have to figure out the type because we're going to have to do some scaling and typecasting. So mtype equals 1. So this is where mtype comes in handy because we're going to output. So we're typecasting to int 8 for mtype 1. So mtype is 1, means typecast to int 8. And then we go get that memory. So base plus the offset times the scale. And again, because the scale is 1, it's optional. Close the typecast. Put a new line. So in the sample, everything was on its own line. So if mtype is 2, then I know to typecast to int 16s, base plus the offset times a scale of 2 for int 16s. A new line. The only other type should be a type 3, so I'm just going to say else, but this is but if an n type is 3, I don't know why I keep wanting to do that, then I typecast int 32, base plus offset times the scale for int 32 is 4 bytes per. New line, endif. So the only thing that we're doing right now is printing out in decimal. We're going to have to figure out how to print out the values in different styles in a future version of this program. But now we're printing out all of those values. The one thing that we're not printing out is that final extra value, which is the calculation cell. So all this does is print out the cells within the selected size, but it does not account for the extra. So here's a cool trick. When ECX is equal to S, equal to the selected size, this loop actually fails. So if they selected 10, then when we get up to an index of 10, the loop fails. But what's magic about the index of 10, if they selected 10, is that's actually the index of that extra cell that we magically created. So when this loop is done, ECX is sitting on the calculation cell, and we can use that, which is just brilliant. So let's put out a standard out.put. We don't know. I'll do it the same way, calc. So then we're outputting the calculation cell. We don't have any active calculations, so I'm just going to say calc. But that's that extra cell that we added. So, and now we have to pin it down to its type. So this is a pain, but there's no other way to do it. Fortunately, I can just grab this same thing. And then hopefully Shift-Tab works. Okay, so the magic here that you have to study to figure out, the magic is that ECX, when this loop exits, is exactly on the calculation cell, which is perfect. It's exactly what I want. So I loop through the user specified number of cells, and then I take advantage of the fact that that ECX actually went one too far, but one too far lands it exactly where I want it to be, which is on the calculated cell. Is that not brilliant? Even though I have to do the work over again, that ECX is exactly where I wanted it to be for the calculated cell. So let's try it. So I'll say 5. It's going to add an extra one. If I say int 32, so that's going to add an extra one. That'll be 6 times 4, should be 24 bytes. Now when I press enter, it's going to print all of my data. And notice they're all zeroed out, and that's because of the z-alloc. And then here's my extra cell that I added manually to represent the results of my calculations, which is also printing out. I don't have the ability to edit or actually perform calculations, but I do have the ability now to print things in decimal. And then I have to do Control-C to get out of there. So there, it's 12:01. That's a good start. What do we have? 15, 16. So we have 2 more weeks. But this would be a good time to start farming procedures from your labs. There's no new lab this week, remember, so if you have the inclination and the energy, this would be a great time to go get yourself some procedures. I can tell you the ones that I know immediately are going to be of use. Get int 8, 16, get int 32. Those are all going to be useful because the user is going to be editing. We did an edit cell procedure, super useful. We have a max procedure that we did last week. That one's going to be very useful, and also that will help us do a min. And then we also have a clear screen somewhere which will be useful. And at some point in the semester we did a show binary. If you can find it, you want that. So anyway, these things at the top are all procedures that we have some form of them out there that either are perfect for what we need or can be edited to meet our needs for this project. So anyway, saving that, that's my version 0.1 of my project 2. Hopefully you were able to follow along okay and I didn't go too fast. But anyway, you have the video now, so, and I'll get that posted like I always do. So anyway, thanks a lot for being here. Hope the rest of your week is good. If you have some time to do something you enjoy, hopefully you do. That would be nice. Otherwise, I will be back here on Monday morning next week as usual. So have a great week. You don't have any assignments for this class, but hopefully you take advantage of that time to give yourself a bit of a start and start farming up some procedures that you've already written that you can use in this project. Okay, that's it for me for the day. I'm done. So take care and have a very good week. Thanks, Tyler. Appreciate it.